Hi, this is Sam Cummings, and this is a presentation on the paper Paralyzing Drones via EMI Signal Injection on Sensory Communication Channels. Bottom line up front. This paper covers an attack on drones using EMI injection. EMI injection is electromagnetic interference injection, where an attacker can target a specific frequency to crash commercial drones immediately. The table below shows this attack highlighted in green as it compares to other current anti-drone attacks. The agenda for today, I'll go over the paper information, give a background on drones and EMI, dive into the attack, look at the attack analysis, and wrap things up. This paper was presented at the 30th Annual Network and Distributed System Security Symposium in San Diego, California, back in 2023. The authors of this paper are listed there off to the left. They are John-Ha Cheng, Banji Cho, Jae-Hon Kim, Dongkwon Kim, Youngdae Kim. 4 of these authors were from the Korea Advanced Institute of Science and Technology. I've included a link to the paper and will include it in the description of this video. Commercially available multi-copter drones are very popular today. They're drones like the one you see in this image, and they have multiple use cases. They're used in delivery systems today, as well as firefighting. This paper focuses on the military use of these drones and how to neutralize these drones using the EMI injection attack. In order to really grasp this research, I want to give a background on the essential parts of a drone. And the first component that I want to go over is the Inertial Measurement Unit, IMU. This controls the attitude of the drone, and it has 4 separate sensors. It's got the gyroscope for the roll, pitch, and yaw, the accelerometer for acceleration, magnetometer for direction, and barometer for height. So the IMU consists of these 4 components, or these 4 sensors. The control unit is the second component that's really important to understand. I like to think of the control unit as the CPU of the drone, or the brains of the drone. So it takes data from IMU, the IMU that we just discussed, and it puts all that data into a run control algorithm where it calculates the delta of the current state versus the target state. So it figures out where we are at this moment, where we need to be, and how to get there. And then it sends the appropriate commands to rotors to get to the target state. Communication channel is the last component of drones that I need to discuss, and this is probably the most important in regards to this paper and the attack that they suggest. The communication channel is how data from IMU gets to the control unit. And the big vulnerability of this whole attack and of these drones is that the communication channel is auto-trusted. And so whatever the control unit receives from the IMU in that communication channel, whatever it receives, it's going to trust. And this is a real issue and the real vulnerability that the researchers try to exploit in this attack. And so there are 2 popular protocols used in the communication channel, the IC squared protocol and the SPI protocol. IC squared is simpler, but it's a little bit slower. It's only got 2 wires. It has the SCL and the SDA. SCL is the serial clock line. You can think of this as like a metronome for music. It's a consistent, like a consistent tick. And then the SDA is the serial data line. That's the data. SPI, on the other hand, is a little bit faster and it has 4 wires. It's got the serial clock, the MOSI and MISO, and then the SS. The MOSI is from the control unit to the sensor, and the MISO is communication from the sensor to the control unit, and SS handles addressing. So in summary, this is a good diagram that they included in the paper. You have the control unit off to the left of this diagram, this drone diagram in blue. That's the control unit. And then the IMU is at the bottom right. And you can see the arrow from the IMU to the control unit. That's the communication channel. All right. As far as EMI, electromagnetic interference, the best way I thought to explain this is through example. So say we have 2 wires like shown here. We have wire A and wire B. Wire A has current flowing through it as displayed with the arrows. And I also want to note that wire A and wire B are completely separate. They're different systems, part of different systems. They're not in the same system. So a given fact is any wire with current flowing through it generates a magnetic field. So that's why wire A, it has current flowing. That's why it has that magnetic field around it. And as this magnetic field extends through space, it can reach another wire, say wire B, that's a conductor, right? Can reach that and push the electrons on that wire, causing unwanted voltage. And this unwanted voltage, this is EMI. I hope that makes sense. So again, the only way I could really think of explaining it. But let me know if you need more clarification. All right, moving on. So that was our background. Moving on to the attack. This is the same diagram that we saw before, of the same diagram of a drone. And you can see exactly like what we discussed before. The attack is on that communication channel between the IMU and the control unit. The researchers conducted a bunch of initial tests to see how the communication reacted under certain circumstances. And I have listed the components that they used for the tests. But what's important here is that you see in the image below on the top, you have the normal communication, IC² communication, with stable SCL and SDA. And so you can see that the SCL is at 5 hertz and it's very consistent. And then the SDA is also, it's readable. It's working as should. But below that shows the researchers bumping up SCL to 7 hertz from 5. And even that little jump causes distortions and irregularities where there's non-deterministic bits. And so going from here, they continued on to not just increasing from 5 to 7 hertz. The researchers tried blocking the IC² signals to see what would happen. And the results are shown in the figure on the left. You can see that blocking the signal also affects the communication. On the right is where the researchers disturbed the communication or the IC squared signals by injecting a second external IC squared signal directly into this existing one, which caused more disturbance. And so they found from this that uh, there are ways to distort this data. And because there's no checksum or no, like we just discussed before, how the communication channel, how it's automatically trusted. This is the IMU data that is that comes out of those distortions. So the bottom right is how the IMU data looks when all those signals are disturbed. Uh, it should look like the top left when where no disturbances are there, but again, because of that vulnerability, it it looks crazy like the bottom right. I wanted to include this diagram of how the researchers set up the environment to do the EMI injection. So you have the RF, the radio frequency generator, they have an antenna, your target board, and then oscilloscope and logic analyzer. And you can see from the antenna, that's where they're sending the electromagnetic wave to the control unit, go from there. The researchers needed to find a point of entry for the EMI attack or injection. And it's really just, they needed to find a path to know, like, hey, this is where we can send the EM waves to increase the voltage, which would affect our communication channel. And you can see that they found all these different points of entry, specifically the control unit, boards, processor, and GPIO pins. Yeah, what the entry points are highlighted in red. Okay, now that we have an entry point, the researchers needed to know which frequency was the most susceptible or which one absorbed EM most efficiently. And they found that this is actually control unit board dependent, as in like for example, shown in those graphs, the Arduino board's susceptible frequency was very high compared to the commercial board's susceptible frequencies, which were very low. And now we know the frequency, but how does this all cause a crash? IC squared signals on Arduino run between the range 0 volts and 3.3 volts. And then a bit flip occurs if EMI pushes signal past 0.9 volts or 2.3 transition threshold. So what that means is the boards have a threshold of 0.9 volts to 2.3 volts. So anything above 0.9 volts will be represented as a 1, and anything below 0.9 volts is represented as a 0. So the goal of an attacker is to add voltage so that it goes beyond that 0.9 threshold, so that even though the system isn't supposed to read a 1 at that particular time, because of the EMI, it does read a 1 if it can get the voltage up past that 0.9 bottom threshold. And then the researchers noted that commercial boards like the PixHawk 4 require an additional 1.44 volts to cause distortions. And that's because commercial boards, they have to adhere to the EMS standards, which make it harder to disturb. Okay, now we know, how this attack works. Let's show the attack. So this was an attack on the NPU 6050, and they used the multi-weave flight controller firmware, and this was only at a distance of 0.44 meters. But you can see as soon as they turned on the EMI, the drone immediately started acting all finicky, and if it wasn't held up, it would have crashed. Now this attack, they show is same board, NPU 6050, same firmware, but this time at 2.4 meters. Okay, and now this attack has two boards listening in, and they have the Pixhawk 4 and the Nano board, but they are only targeting the Pixhawk 4. Or in other words, they have the target frequency of the Pixhawk 4 that they found out earlier, and they want and they want to show that you can target specific boards and not affect others. So let's go ahead and watch this. I do want to point out the bottom left is the Pixhawk 4 data, and then in the middle right of the screen, highlighted in red, that is the Nano board data. So you could see that I go back actually, that only the Pixhawk 4 data was affected. The Nano board was not, and this is ideal. This shows, say you have an enemy swarm of drones, right? But you at the same time have your allied drones up in the air. This proves that you can attack your enemy drones at their susceptible frequency and neutralize them, you know, and at the same time, your drones will not be affected. And that's the downfall of a lot of current solutions out there, is they take down drones, right? But they take down any drone, and you don't want to lose your allied drones. Okay, so moving on to the analysis. So this is the power and range of the attack. For the Arduino board, you only need up to 100 megawatts or milliwatts at a distance of 0.84 meters. Pixhawk 4, you need 10 watts at 0.5 meters. And the Mavic Pro, you need 21 watts at roughly 5.5 meters. And so it's estimated to require about 148 kilowatts of power at the distance of 100 meters. and then roughly 310 kilowatts for that same distance for DGI. And now that may seem like a lot, it is, but compared to conventional EMP weapons, right, it's really not that significant and it's pretty feasible to accomplish. Okay, response time. As you saw in the videos, it's very, very fast. It's pretty much instant. It's a single window, which is usually 0.025 seconds. It defeats detection because detection needs about 80 samples in about 2 seconds. This would happen way before any detection. And then recovery needs about zero point 0.2 to a whole second, which again, this happens in 0.025 seconds. And then this just shows the results, the different sensors, and how as soon as you attack, that next sample is when all the data goes haywire. All right, so in conclusion, we went over the paper and went over the EMI injection attack on communication channel. And that's between, remember, the IMU and the control unit. There are a couple advantages. Attack frequency is control unit board dependent. So that's when, you can only affect your enemies and keep your friendly drones up in the air. And the attack immediately incapacitates the drone. The researchers did mention a countermeasure, which is metal shielding. But for one, it's more expensive. For two, it heats up the board significantly, and it can also interrupt wireless communication that needs to happen. So yeah, these are my sources, and I will post these in the description as well. I highly suggest looking at this site, google.com, view paralyzing drones via EMI. That's where they posted, this research and the videos. But yeah, thank you for watching.